Well, greetings everybody. Here's what you missed when we covered Chapter 1, Day 2. What I did is I fielded any questions that they might have had over Worksheet Day 1. My answers to that are on the next few slides. So if you have that worksheet, you could pause this video once you get to those screens and check your answers. You will need to get in and make up a homework quiz, because right now it's sitting in the computer as a NHI, which means not handed in, and it's counting as a 0 right now. And then I do need to cover Section 1-2 over the different types of numbers that we're going to talk about throughout the year, and then the properties of some real numbers, and of course we'll end it with the worksheet. Hopefully you have the day's notes sitting right in front of you. So here goes. There happens to be some of the answers to worksheet number 1, that order of operation worksheet. So there they are. Like I said, you can always backtrack and pause the video and check your answers. There's also a page. I'll try to slide that out of the way a little bit so you can see the true answer. I'll slide this out of the way again and down a little bit so you can see the answer. And there's the final few. Like I said, that's the answers of worksheet 1. That's just a blank page so I can answer class questions. Hey, you might be wondering, Mr. Harris, why do you got a picture of Charlie Brown sitting on your computer right there? That's what I'm going to feel like a little bit today on this lesson. There's not a lot of interaction in this lesson. I'll ask you some questions, of course, to try to keep you engaged, but there's just a lot of factual information I need to toss your way today. So a little bit I'm going to feel like Charlie Brown's teacher. So hang with me so I don't sound like womp, a womp, a womp. So here goes. Look at your classroom notes. I just need to talk to you about the different types of sets of numbers. So these are just facts. And follow along with me as you go. The natural numbers, those are the counting numbers. If I gave you a box of rocks and asked you to start counting, you'd go 1, 2, 3, 4. Well, you would say 1, 2, 3. Notice that 0's not included, -1, -2, -3. There's no fractions, there's no decimals. A lot of notation that we're going to use this year. Notation that you're going to see, whenever it says the set of numbers that we're talking about, you'll start off with a brace. I like to call them cool parentheses, but really they're called a brace. And the set of numbers is going to be 1, 2, 3, dot, 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 and then your brace. The symbol that we use for the natural numbers is an N. So what I'm going to do is I'm going to start with the small set of numbers and make them bigger. If I take the natural numbers and add 0, I get what we call the whole numbers. So on the number line it would look like this. There's a 0, there's a 1, there's a 2, there's a 3. As a set, you'd have that brace, and there'd be a 0, 1, 2, 3, dot, dot, dot. With the symbol, there would be a W. W for whole numbers. So what I've got going so far is I've talked about the natural numbers and the whole numbers. If I give you a whole number, it's automatically a natural number. Kind of works that way. Now, if I go another step, the integers are going to be the whole numbers and the opposites. And included in there, even though it doesn't have an opposite, is 0. So when we talk about integers, 0, 1, 2, 3, but I can also include their opposites. As a set, it looks like this. I got dot, 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 meaning I have numbers that go to the left also. I'm going to go -2, -1, 0, 1, 2, dot, dot, dot. Now common sense would say the symbol for integers is an I, but it's not. It is a Z. They use I here in just a little bit for a different set of numbers. Okay. Now, the next set, and getting a little bit bigger then, would be what we refer to as our rational numbers. Rational numbers would be this. This would include our fractions. This would also include our decimals that terminate. Decimals that terminate. These also include our decimals that repeat. Some examples of the rational numbers: the number 2/3 would be a rational number. For the simple fact, it's a fraction. The number 1 7/10, that would be a fraction, so that would be a rational number. A number like 4.27, the decimal stops, so it's a rational number. A number that looks like this, 3.12 repeating. There's a distinct pattern to it. That's an example of a rational number. Now you would like to think the symbol for rational numbers is R, but we're going to use that one here in a second. It is a Q. So if you think about my set of numbers so far, I've got NW, I got the integers, and I've got the rational numbers. It works like this. If a number is a natural number, like 3, it's automatically a whole number. It's automatically an integer. It's also a rational number because I could think of 3 as 6 divided by 2, as 9 divided by 3. So it's also a rational number. Okay. Now I'm just going to give you the definition of irrational number. These would be our non-terminating decimals. Technically, it's our non-terminating, non-repeating decimals. Okay? Like pi would be an irrational number. It has no pattern on it, and it goes on forever. Other irrational numbers, the square root of 2 would be a rational number. The square root of 3 would be an irrational number. The square root of 5 would be an irrational number. You might think, but how about square root of 4? Well, the square root of 4 is 2. 2 is a natural number. So there's what we got so far. The symbol for irrational numbers is, what you're thinking, an I. So there's what we got so far. And if I go on to my next page, the real numbers, that would be all of the rational numbers and all of the irrational numbers. A number cannot be both irrational and rational. It's one or the other. The symbol for a real number is the R. Okay? So what I'd like to do is, I'm giving you a cheat sheet here that you could use on your homework and on your homework quizzes. So just as a form, if it's a natural number, it looks like this: 1, 2, 3, ... If it's a whole number, 0, 1, 2, 3, ... If it's an integer, that's our -2, -1, 0, 1, 2, and they continue in both directions. So if something's a natural number, it's also a whole number. It's also an integer. Rational numbers, there comes our fractions. And then decimals that stop, I'm going to call them nice decimals. Decimals that stop, decimals that repeat. Remember the irrational numbers, these are our non-repeating. A lot of times in class, I'll call these the ugly decimals. There's no pattern to them. And then real numbers is our rationals and our irrationals. So that's just some facts I had to throw at you guys. Jump over to your next page then. I'm going to give you some numbers. We're going to decide what sets they belong to. So on my left side of the board and on your sheet now, we're going to have the set of numbers that have the natural, the wholes, the integers, the rationals. I'm going to put the irrational over here out of my way a little bit, and then the real. All of these numbers in here belong to the real numbers. So I could put an R with all of them. But here's how we're going to attack this. Look at negative 11/3. It's not a natural number because you would not count by, you wouldn't say that if I asked you to start counting. It's not a whole number. It's not an integer. The first set that it belongs to is the rationals because it's a fraction. So I'm going to say that this is a rational number. And then like we said, every one of these numbers is a real number. Number 2, the square root of 25. The square root of 25 is really 5. So I'm going to come over here and figure out the first set it belongs to. Well, 5 is a natural number, a counting number. So it's a natural number. Now watch how this works. Since it's a natural number, it's automatically a whole number. If it's a whole number, it's automatically an integer. If it's an integer, it's also a rational. Because I could write 5 as 5 over 1, 10 over 2, 15 over 3, and it's a real number. Notice that the irrational is not used if the Q is used. Number 3, here's a repeating decimal. These guys right here can't have decimals, so they're out. So this would be a rational number and a real number. So there's where we're at so far. Number 4, 0. It's not a natural number, but it is a whole number. Since it's a whole number, it's an integer. I could think of 0 as 0 over 1, 0 over 2, 0 over 3, so it's a rational number, and it's a real number. So I hope you see how this is working. 192.0005, these three are out because it's got decimals in it. This decimal stops, so it's automatically a rational number and a real number. Number 6, the square root of 36. Well, square root of 36 is really 6. So I've really got 6 over 9, and that reduces to 2/3. Well, 2/3 is a fraction, so these three are out, NWZ, so that makes it a rational number and a real number. Keep on keeping on. Pi, you guys worked with pi last year in geometry. It's definitely not something you could count by. It's not a whole number, it's not an integer, it's not even a rational number. It's an ugly decimal. It goes on and on and on. So it's an irrational and a real number. 15/3, that is really equal to 5. 5 is a natural number. Since it's a natural number, it's automatically a whole number. It's automatically an integer. It's automatically a rational number, and it's a real number. Number 9, I got the opposite of the square root of 81, and that's negative 9. Well, I'm going to go see which it belongs to. So it's not a natural number. If you started counting, you wouldn't count by negative 9. It's not a whole number because it's not positive, but it is an integer. It's also a rational number, negative 9 over 1, negative 18 divided by 2. Since it's a rational number, it is a real number also. Keep on keeping on. Here's my number 10. Square root of 25 is 5, so this is really 5 over 2. Well, the top three are out, so it's not any of those. The first one it belongs to is a rational number and a real number. If I look at the square root of 42, it doesn't break down nicely. If a radical doesn't break down nicely, it's an irrational number and a real number. And then last but not least, square root of 5 over 2. Well, the square root of 5 is a square root that we don't know. That automatically makes it an irrational number and a real number. So that takes us down through 12. Like I said, guys, that's just facts about some numbers. So keep those handy so you can refer back to them once you get your assignment. Hang with me on this next little part. I'm going to give you some little side notes to write on this also to help you out. Properties that we're going to need to know and use throughout the year. The commutative property says A plus B equal B plus A. That doesn't help me a lot. Well, I can come back and say 3 plus 5 equal 5 plus 3. That helps me a little bit. But the commutative property means that you're going to switch places. That's what the commutative property means. So if you kind of look around, if I look down here real fast, if I look for anything that switched places, 84 plus 16 equals 16 plus 84, they switch places. That makes this guy the commutative property. And since we're working with the addition, I'm going to put of addition. So if anything switched places, then that makes it the commutative property. The associative property always deals with parentheses. The associative property means that the parentheses moves. So let me come down and see if I could find any where the parentheses move. The order here goes 6, 8, 5, 6, 8, 5. So there's nothing switched. But notice that the parentheses were around the 6 and the 8. Now they're around the 8 and the 5. So this is the associative property, and it's still in with multiplication. Notice I use 5 letters to abbreviate the associative property. Don't use 3. When I look down a little bit more, I'm going to see if I can find another associative property. So when I look down through here, looks like maybe right here, the parentheses moved. So here's another associative property. But this time I'm dealing with addition. Okay, now the identities I'll clean up a little bit more. The identity just says this. I'm thinking of some number. What could I add to it to get that number? Well, you would say, duh, Mr. Harris, 0. Right. The additive identity is 0. If I'm thinking of some number and I ask you to multiply by some number to get me back to 5, well, that's 1. So the additive identity is 0. The multiplicative identity is 1. Here's the hard part, though, inverses. The inverse says, what's it take to get 0 using addition? And what's it take to get 1 using multiplication? Well, to get 0 using addition, if you would, right here, where in this box here, put the opposite. The opposite. Here's what that's saying. 3 plus some number has got to give me 0. Well, what's that number going to be? It's opposite, -3. So that's where that comes from. The multiplicative inverse right here is a little bit more of a challenge. It says this, 3 times something equal 1. 3 times something equal 1. Well, just since we're on a video, whenever you want to turn a number into 1, you multiply by its reciprocal. So the inverse of multiplication is the reciprocal. And this thing cutting out just a little bit. Okay, but the reciprocal. I'm not going to worry about the closure property because everything we do is going to pertain to the closure property. And the distributive property you've done 100 times. It just says this, if there's a number out front of something, I can distribute it and get rid of the parentheses. So look at number 14, 16, and 18. Notice that I'm going 7 times 9 and 7 times -5. I distributed that 7. So this, my friends, is the distributive property. This one's just written in the back side, but it's still 12 times 6 and 5 times 6. So this is also the distributive property. Number 18, 8 radical 11 plus 5 radical 11 is 8 plus 5 radical 11. They just flip sides on us. But that's another distributive property. The only two I didn't do is number 17 and 20, so here they go. -7 plus 7 equals 0. Whenever you get to a 0 or a 1, that is some type of inverse. Since I'm using addition, this is called the additive inverse. Here's my number 20. Notice these two guys are reciprocals. So if I look up here, it's some kind of an inverse. So this is going to be some kind of an inverse, but it's going to be the multiplicative inverse, M-U-L-T. Okay. And then I'm almost done with the lesson, so hang with me there for a little bit. I think I've got 4 problems to fly through with you. Oh, and then I have this. This is not on your notes, but I have some problems like this on the homework sheet. Here's what I'd like to do. It says, for each of the following, state the additive inverse, aka the opposite, and then state the multiplicative inverse, aka the reciprocal. Okay. Well, the additive inverse of 5 is just the opposite of 5, -5. The multiplicative inverse is the reciprocal of 5, 1/5. The additive inverse of -3, +3. The multiplicative inverse of -3 is its reciprocal, -1/3. For 2/5, the additive inverse is the opposite, -2/5. The multiplicative is 5/2. The reason that is, guys, 2/5 times 5/2 is 10/10, which is 1. Now, 2 and 2/5 is a little bit different. The additive inverse is pretty darn easy. It's -2 and 2/5. But now I got to find the reciprocal of that. So kind of a trip down memory lane. I need to turn 2 and 2/5 from a mixed fraction to an improper fraction. To do that, you do this. I'm going to have to go 5 times 2 plus 2. So let me kind of write that out with some space. I'm going to go 5 times 2 plus 2. So 5 times 2 is 10. 10 plus 2 is 12 over 5. This and this are the exact same number. Now I need the reciprocal of that, so I got 5/12. Let me do another one real fast. 3 and 3/4. What I'm going to do is 4 times 3 is 12. 12 plus 3 is 15. So that number would be 15/4. The multiplicative inverse of that, 4/15. So there's a couple of those on your homework assignment. And then we're oh so close to done. On 21, I just wanted to review the distributive property with you and combining like terms. So here goes. I'm going to distribute this 8. So I've got 24a minus 8b plus 8b minus 4a. I did a good job of watching my signs because I'm trying to end the video with you too. This is a like term and this is a like term, so I've got 20a. Those two add out, so boom, there's my answer. Now the others, you can use your calculator on, if you got it. If not, I'll just show you how you can do it without working too hard. 1/5 times 4, well, that is 1/5 times 4 over 1. To work with fractions, just multiply straight across. So this becomes 4/5 j plus 2/5 k minus 6/5 j, I'm distributing that to everything, plus 3/5 k. So there's where we are so far. Now we just got to go find like terms. So there and there are like terms. If you have your calculator, you can go 4 fraction key 5 minus 6 fraction key 5, and you're going to get negative 2/5 j. If I go 2/5 plus 3/5, they got a common denominator. So 2 plus 3 is 5 over 5 is 1k. So there's that solution. If you got your calculator on number 23, you can use it, but there's a better way. What I'm going to do, instead of going 12 times a over 3, I'm going to reduce first. 3 goes into 12 4 times. So 3 goes into 12 4 times. 4 times a is 4a. And then what I'm going to do is the same thing, but I'm going to use the 4. Let me get that out of the way. 4 goes into 12 3 times, b, so minus 3b. Okay. Like I said, if you got your calculator on these, it's even easier. I don't have my calculator in front of me, so when I distribute here, I'm going to get 8.4x minus 6y, and there's an invisible 1 right here. So I've got minus 10y plus 4.3x. Combine your like terms, 8.4 and 4.3, so I've got 12.7x minus 16y. Okay? That is our lesson over section 1-2. So you should have all the information that you need to finish up your assignment. Good luck on it.